Chapter 9 here. Next exam stuff, I think. All right, so in this chapter, we're going to talk about, go with the liquid state. Seems like a good thing that we're going to talk about. So we're going to talk about water and some other properties of liquid. Obviously, when we talk about the liquid state, everybody is still packed in there fairly close to one another. There's a little bit more room for movement. There's more energy associated with those things. That's why we associate fluids, our liquids, as being fluid, and they can kind of move around, as opposed to when they get into the solid state where they sort of just lock up, if you will, as they have much less energy. So the first thing we're going to talk about, though, are different types of forces and how they affect things like melting points, boiling points. The first type of force that we're going to talk about are intermolecular forces. And intermolecular forces are really the forces that hold one molecule together with another. And for the most part, as we'll talk about, all intermolecular forces are a result of a pretty simple sort of interaction, and it's basically electrostatic interaction. It's the positive side of one molecule is basically attracted to the negative side of another. So this is, again, how, for example, something like two water molecules will hold each other together. Water, which is polar, hydrogen more positive, oxygen more negative. So the negative side of one water molecule is attracted to the positive side of another. That is, as we'll talk about shortly here, what's known as hydrogen bonding, which is an intermolecular force. The intermolecular forces are really the properties that determine things like how small or large a melting point or boiling point is. So for example, if we were to go to heat water up, we would need to really break the bond between the two water molecules to allow this water molecule, for example, and this one, to separate out and say go into the gas phase. And that's what happens at the normal boiling point of a substance. Now, depending on how strong that attractive force is, we will see a much higher boiling point or melting point if it's a very strong association. So if this is a really strong association, it's going to take more energy to get those guys to separate out from one another. The result of that is, again, a higher melting point, boiling point. Vice versa, if you have something that is held together by like a super weakish type of force, it's not going to take a lot of convincing. It's not going to take a lot of energy to get those guys to basically separate out from each other. And that results in a much lower boiling point or melting point. So intermolecular forces are really responsible for how molecules basically interact with themselves. It's also responsible for how molecules interact with other molecules. It's also the basis of why certain things are soluble in other things. So things are soluble in each other with this idea of like dissolves like. So things that use very similar intermolecular forces will be soluble in each other. So something, for example, uses hydrogen bonding. It will work really well with something like water, which also uses hydrogen bonding with itself. So they're able to interact very easy for one another to interact with each other because they are using this same type of force. So only when things are trying to use widely different sort of intermolecular forces, for example, that things tend to not be soluble in each other. And that's why when we take something that's polar and non-polar and try to put them together, they are using completely different types of intermolecular forces, as we'll talk about here in a bit. And because of that, they have no way to maintain that interaction with one another over a long period of time. They'll sort of separate out like oil and water, right? They will separate out from each other. Oil and vinegar, like salad dressing, right? You could shake it up, it'll mix for a short period of time, but if you leave it settle, it will basically all kind of settle out from one another because it has no way to maintain those sort of interactions. So intermolecular forces are really important for a lot of how molecules interact with another. They are also the things that we talked about at the end of the last chapter when we talk about real gases, where under those sort of real gas situations, this is van der Waals interactions. This basically, when they interact with one another, they can affect things like pressure when we do have that real gas sort of situation. Now, intermolecular force is different than intramolecular forces. Intramolecular forces are the forces within a single molecule that basically holds it together. So intramolecular forces are within the molecule or compound. So for example, if we just took one water molecule, it is the covalent bonds that happen between the oxygen and the hydrogen here that hold this one particular water molecule together. That is the intramolecular force. And intramolecular forces are like covalent bonding, also like ionic bonding, which is how ionic compounds are held together, opposites attract. They're really, really strong forces. They are much stronger than any intermolecular force that we'll talk about. So intermolecular forces are much weaker than intramolecular forces. We know that by the simple example of water. So again, we have that interaction with water between the positive of one and the negative of another doing hydrogen bonding. And what happens when we heat water up at its boiling point is we end up breaking this bond here first, and that is the bond between the two separate water molecules, which again allows them to go into the gas phase. And that tells us that the intermolecular force is much weaker than the intramolecular force. You only need to get about 100 degrees Celsius to get that thing to basically break apart from one another. If it was the opposite and the intramolecular force was weaker, when we would go heat something like water, you would start breaking these bonds first. And then you would have hydrogen gas and oxygen gas, which would not be great if you're trying to boil some water for pasta for dinner. So you wouldn't want to make that, I suppose. So we know, again, just by that simple example there, that definitely the intermolecular forces are going to be much weaker than any intramolecular force that you have. Any questions on that there? All right, so what we're going to talk about here is really intermolecular forces. So all these that we're going to go over here are intermolecular forces. The first type of intermolecular force is what is referred to as a dipole-dipole interaction. And you might remember the word dipole from when we talked about bonding. And when we talk about bonding and something that has a dipole, that is usually something that has, as we talked about, a dipole moment, which essentially means you have a polar molecule, and overall that molecule has unequal sharing of electrons, which means, in a very simple drawing, there is a positive side of that molecule and a negative side to that molecule because of the overall unequal sharing of electrons that are happening in a polar molecule. Because it's a polar molecule, because it has a dipole moment, no matter what you do to that molecule, it's always got a positive side and a negative side, which means when it comes across another polar molecule, they are good to go in terms of bonding, and they will be able to be attracted to each other via the opposite charged sides of the molecule. So dipole-dipole interaction are the basic and interaction that occurs with polar molecules. So this is basically the ones that occur with polar molecules that cannot, as we'll talk about, hydrogen bond. So these are polar molecules that sort of lack the ability to hydrogen bond, but they're still polar. They still have that positive and negative side. And what happens when we have a bunch of polar molecules together in a solid, they do try to align themselves in a way that will maximize the attractive forces between the positive side and the negative side of the molecules, and minimize sort of positive sides being near positive sides and negative sides near negative sides. So as they kind of settle down into a solid sort of structure, what happens is actually the molecules start moving around, kind of moving around and vibrating around until they find sort of an acceptable situation that once again maximizes that attractive forces and minimizes the repulsion forces. Obviously, no matter what you do, if you kind of cram together a bunch of polar molecules, you're always going to kind of have a positive near a positive, a negative near a negative. But once again, they'll keep sort of wiggling around, if you will, until they soon kind of maximize those attractive forces rather than those repulsive type forces. And that's what we see here. This is their basic dipole-dipole interaction. And in a sort of situation, they do try to maximize those opposite attractions while minimizing those repulsive type attractions or repulsion type forces. Now, another type of interaction is what is sometimes referred to as an ion dipole interaction. And an ion dipole interaction is an interaction between pretty much what it sounds like, an ion and a polar molecule. So this is how a polar molecule interacts with an ion. And that's also why polar molecules and ions are pretty soluble in each other, like water, for example. This is like the process that occurs when you dissolve some type of ionic solid in water. Water, again, is polar, which means it has a dipole moment. And when you dissolve something, say like sodium chloride in water, what happens again is you have your two ions. And water works really well with that because the negative side of water is able to surround the positive ion, while the positive side of water is able to surround the negative ion in this case. And that is why they are fairly soluble in each other, and water is a pretty good solvent for a lot of ionic compounds because it basically can interact very well with them. They're able to surround them. So again, ion dipole forces allows polar molecules to basically interact well with the ions through their opposite attraction. Ionic compounds usually have low solubility in nonpolar solvents, and that is because if you try to do this with a nonpolar solvent, as we'll talk about, nonpolar pretty much means there is no charge, right? So nonpolar molecule has overall equal sharing of electrons over the entire molecule, which means there's no side that's more positive, there's no side that's more negative, kind of like a neutral sort of molecule. And that makes it pretty troublesome for if you're trying to dissolve an ionic compound in it, because it has no real way to interact well with it because there's no opposite attraction that's going to happen, as opposed to what we see here with water. Now, dispersion forces is another type of intermolecular force, and dispersion forces are pretty much your weakest type of force. And dispersion forces are usually as well pretty much your main type of intermolecular force for nonpolar molecules. So this is how pretty much nonpolar molecules work with other nonpolar molecules. And we can make a dispersion force through several different types of interactions that can happen. But what makes them really weak is that they are typically temporary type of forces, and they do have to rely upon something happening to allow them the ability to sort of interact. So one way you can sort of have that occur is through what is referred to as an induced dipole. And an induced dipole is the separation of charge in a nonpolar molecule that's caused by something that has a charge. So if you sort of roll up, for example, an ion-induced dipole interaction, so if you have a neutral molecule here, which is nonpolar, and you throw a positive ion near it, temporarily what's going to happen to this nonpolar molecule is the electrons are going to head towards that positive ion because they're going to be attracted to it. So now this nonpolar molecule, which normally does not have any type of separation of charge, will temporarily gain a separation of charge within it and now have a negative side and a positive side. And it does give it a way to interact with that ion. But the problem is if that ion just kind of moves away, that interaction and that guy's going to go back to their electrons, their normal distribution, and it's no longer going to have that sort of charge. And same thing would happen if you took something like a polar molecule and you rolled it up against a nonpolar molecule. Again, you will get that sort of induced dipole in the nonpolar molecule and a temporary way for it to interact. So it kind of goes back to what we were just talking about. You can mix, right, oil and vinegar salad dressing, and it will stay mixed for a bit. But over the long period of time, it is such a weak interaction as this one sort of makes an interaction, breaks an interaction, makes another interaction. There's no way to maintain that interaction over the long period of time. And eventually what will happen is they will sort of separate out from each other. That's also why, right, when we have like an oil spill in the ocean, the oil just starts floating on the surface eventually, right? And that's because it cannot really work really well with the water, which is a polar molecule over the long period of time. So one way that dispersion forces works, and this is why anything, for example, polar molecules, non-polar molecules could technically use dispersion forces, but that's sometimes not their main sort of intermolecular force. Like polar molecules, dipole is their main sort of intermolecular force. You can do an ion-induced dipole, a dipole-induced dipole, and there's also another way that you could kind of do these very weak and temporary interactions. And this is what is sometimes referred to as an instantaneous dipole. And this is caused by basically the ease at which the electrons in a nonpolar molecule may decide to take a vacation on one side of the molecule or another. So for example, if you had, say, two nonpolar molecules here, and in this first nonpolar molecule on the left there, if all the electrons, for whatever reason, decided to sort of migrate over there to the right-hand side of the molecule, which they could do because they are flying around randomly, so they could find themselves at one point all kind of in the same sort of area of the molecule, that would create a temporary sort of separation of charge in that nonpolar molecule, which if it is now still near the other nonpolar molecule, will cause the electrons in this guy to decide, I would like to go away from that negative side of that molecule, which is then going to turn that second nonpolar molecule into a molecule that has a separation of charge. So now these two normally nonpolar molecules, equal distribution, now have unequal distribution. I guess I should actually draw that for better here. So we'll make the negative on the other side, which is where they should go. There we go. And now we can have an interaction between these nonpolar molecules, between the positive side of one and the negative side of another. And that's what is referred to again as an instantaneous dipole. And polarizability is the ability of the electrons basically to do that. Again, this is going to be a weak interaction because as those electrons come back from vacation, it's going to kind of break apart and make new interactions and break apart and make new interactions. And again, this is why it's quite a weak sort of interaction. But it does increase in terms of its strength. So when you're talking about dispersion forces, although they are weak interactions, typically the main force for nonpolar molecules, the strength of a dispersion force actually increases with molar mass. So if you're comparing, say, one nonpolar molecule with another, and you want to know something like which one might have the higher boiling point or lower boiling point and stuff like that, the one that has the greater molar mass would probably have the higher boiling point in that case because it has a lot more electrons. So the only way you could have a more molar mass is to have more atoms. More atoms means more electrons, and more electrons means there's a greater chance of those electrons kind of moving around from one side to the next. And it also gives more areas where those electrons can kind of interact with one another. So when comparing this sort of weak intermolecular force between two molecules that use the dispersion forces, the larger the molar mass, the stronger the dispersion force will be. It's still a very weak interaction, but in comparison of weak versus weak, bigger molar mass, greater chance of electrons kind of dispersion over the place, and stronger interaction. Any questions on that? So dispersion forces, like I said, pretty much your main root of attractive forces between nonpolar molecules. Polar molecules, again, are going to use dipole interaction, which is much stronger than dispersion forces. And another type of interaction, as we'll talk about in just a second, but dispersion forces, which are dipole-induced dipole, and all these guys are sometimes referred to as van der Waals interactions. And van der Waals, again, is that guy that had the crazy looking ideal gas law there, where we took into these intermolecular forces into account. So when we talk about dispersion forces, they are on the weaker side, which means things that use dispersion forces, which are nonpolar molecules, typically have very low boiling points and melting points. That's why a lot of organic molecules, which are pretty much carbons and hydrogens and nonpolar molecules, several of the first ones are things like methane, propane, butane. Those are all gases, and they're gases because they're basically held together by super weak intermolecular forces. Also why if you take organic chemistry, they usually throw you in a fume hood because most organic molecules are very volatile, which means because they're held together by these really weak forces, even in a liquid form, they could go into the gas phase very, very easily, and they're usually quite flammable in that sense as well. So they usually have you work in a fume hood just in case that should occur. So here's our instantaneous dipole, again, sort of the one atom inducing a dipole in the next. And now we have some interaction happening between our two molecules. Now, the last type of interaction, which is really a dipole-dipole interaction, but it is classified sort of by itself, is what is referred to as hydrogen bonding. So this is really a type of dipole-dipole interaction. And it is a bond between hydrogen and an electronegative atom like nitrogen, oxygen, or fluorine. If you look at the periodic table, NOF there is upper right of the periodic table, which means it has very high electronegativity. So when you have a hydrogen that is bonded to one of those guys, you will get a quite big polar type bond. So if you remember when we did like the difference in electronegativity between, say, hydrogen and fluorine, it was like 1.9 difference, and 2 is like an ionic bond, right, where electrons are transferred. So that's quite a pretty big separation of charge is going to happen, and that makes these hydrogen bondings pretty much your strongest intermolecular force you could have. So something that can hydrogen bond is kind of the strongest intermolecular force you could have. Again, dipole is pretty close because it really is kind of the same thing. And again, on the other end of the extreme is our dispersion forces, which is the weakest that you could have. So things that can hydrogen bond will definitely have higher boiling points than things that cannot hydrogen bond. Things that can do dipole will still have higher boiling points than things that are dispersion forces and basically holding together. Now, it's really important, the idea that the hydrogen here does need to be directly bound to nitrogen, oxygen, or fluorine to have the ability to hydrogen bond. Sometimes people think based on the name that you just need a hydrogen. So for example, if you had something like this, although this guy has a ton of hydrogens, none of them could hydrogen bond. Because that hydrogen is actually bound to carbon, and the carbon-hydrogen bond is actually a nonpolar bond. So there is actually no separation of charge that's happening with this guy. So although he has a bunch of hydrogens, no hydrogen bonding would be happening in this case. This guy's actually a nonpolar molecule, which means he's going to actually be using dispersion forces as its method of interacting with things. That is why something like water here has the ability to hydrogen bond, because it's a hydrogen that is directly attached to an oxygen, which creates that ability to hydrogen bond with itself with other molecules, for example, like methanol, which is an alcohol, can also hydrogen bond. And again, they'll get some type of interaction between the hydrogen and the oxygen in that particular case. That's why something like methanol there is actually soluble in water, because methanol is small. It has that OH group just like you find in water, which allows it to interact well with it, even though it has carbons and hydrogens, which is non-polar, but that small little polar part of this molecule allows it the ability to interact well with water, and they're going to mix really well together. Now, if you try to do that same thing, for example, with not methanol, but you know, you add a lot more carbons there. Let's keep going this way. That should work, I think. So clearly all this is carbons and hydrogens, and all this part of the molecule is pretty much non-polar. This part here is polar. So when this guy now goes to try to work with water, it doesn't work so well, because frankly, you got this big part that's in the way there that's non-polar, sometimes referred to as steric hindrance, which means it gets in the way of its ability to interact well with water, even though it still has that OH group. And something like that would be not very soluble at all in water, even though it still has that OH group, because of the big non-polar part that's there. So as we'll talk about in a later chapter, in order for something to basically dissolve in water, you have to replace water interactions with other water interactions with something that's very similar. So water is not a very big molecule, and it has the ability to hydrogen bond. So although this guy does have the ability to hydrogen bond, because of that big non-polar part, it just kind of gets in the way. It's not going to work well or mix very well together. It's kind of like, again, if you had a garage and you put a car in there, it's going to be okay. Probably, as long as you stop. You try to park a semi truck in there, maybe get part of it in, but it's really not going to fit so well, because it's quite big for the space that you're trying to park it in. And that's what happens in these situations when you get really big molecules. Even if they do have this little part that can interact, it's not going to be able to interact really well. So for example, if I had something like ammonia here, can ammonia hydrogen bond? Ammonia can hydrogen bond. It has a hydrogen that's directly attached to a nitrogen. It's also a polar molecule, right? Ammonia has an unsymmetrical geometry. So this guy could hydrogen bond as well. So hydrogen bonding, again, the strongest that you could have, dipole, pretty close. And then again, the weakest interaction is our dispersion forces. As I sort of alluded to here, again, these are the things that really do play the biggest role in terms of how things interact with one another, why certain things, again, are soluble with each other and some of the things are not soluble with each other. So and that's why we do that idea, as we'll talk about, like dissolves like. So polar things and polar things are really soluble in each other. Ionic things and polar things are soluble in each other because they could do the ion dipole interaction. Something that people sometimes miss is the idea that nonpolar things and nonpolar things are soluble in each other, because they're both using dispersion forces. So although they're using a super weak type of interaction, they're both using the same type of interaction, so they're able to interact with one another. So nonpolar things and nonpolar things are also soluble in each other. It's really when you cross over from polar to nonpolar that you do run into some problems, because again, they're using very different types of intermolecular forces. Any questions on any of that there? Here's again some hydrogen bonding with our water molecules. So let's talk a little bit more about liquids and some of the properties of liquids. Liquids obviously are much closer together than gas molecules, as they have lost energy, so they're no longer flying around. They no longer can escape each other as they were flying around, so they kind of stick to each other and drop into the liquid phase as they are losing that energy. Viscosity is the resistance of liquid to flow, and again, it's related to intermolecular forces. Water has a low viscosity, motor oil has a high viscosity. Viscosity does decrease with temperature, and the idea there is obviously resistance to flow, so it's not going to flow very well, but if you heat it up, more energy, right, things can start moving a little bit more, and it's going to start to flow a lot better. Now, there are some different types of forces that play a role in how things like water and other liquids sort of interact. There are cohesive forces, and cohesive forces are the forces that have attraction between a single substance. So this is how one substance interacts with itself, and that is cohesive forces, which is our hydrogen bonding. Adhesive forces are the attractive forces between different molecules, and as we will see shortly, this is one of the reasons for our meniscus and why the water climbs the wall. As the water, for example, is more attracted to the glass container there than the water itself, so it starts to rise up the wall and creates that meniscus that we see. Surface tension is the elastic tendency found at the surface of the liquid. So when we have at the surface of any liquid, so for example, if we have water molecules drawn as wonderful circles here, and we have some water molecules that are sort of under the surface, when we look at a water molecule that is under the surface, it is going to have some attractive forces or hydrogen bonding pretty much all around it. So it's going to be attracted to everybody around it, top, bottom, sides, and everything like that. But when you look at the water molecules, say at the surface, they're pretty much just going to be attracted to everybody to the sides and down. Nobody being attracted to the top. So what that's going to do basically at the surface is stretch it, right? Kind of stretch it out and make it a little bit tighter there, as there is no sort of attractive force kind of pulling it up, just kind of pull it sideways and down. So it is higher in terms of the surface tension for liquids that have a greater intermolecular force. So the stronger the intermolecular force between the different molecules are going to pull it tighter, and you get a much stronger sort of surface tension that's going to happen. Like you can lay a paper clip down on some water and it'll kind of float there. Surface tension is greater than water than other liquids because of the really strong hydrogen bonding that occurs with water. Also why some bugs can just walk across the surface, right? Without having any problems because of that surface tension, right? Why you pour a liquid, right? And you keep pouring it and it looks like it's above the top of the thing, but it's not spilling until you go cool. And then you do that and you break the surface tension and it all falls all over the place. These are fun tricks. So this are water molecules, and once again, because of that strong attractive forces to the side and down at the surface, we get that surface tension as opposed to more sort of even sort of distribution of attractive forces below the surface. So what about soap and water and what happens with all that? If you add soap, and what soap is actually, there's two parts to soap. There's a really long part, and I'll just draw it in line structure. These are all just carbons and hydrogens, basically. So all these are carbons, and there's hydrogens all the way across here. This is the nonpolar part of soap, sometimes referred to as the nonpolar tail of soap. And at the other end of soap, you have this polar part, which is sometimes referred to as the polar head of soap. So soap actually has two parts, a nonpolar part and a polar part, which works really well for how soap actually works, because most dirt is nonpolar. So most dirt is nonpolar, which means when you use soap, the carbon side of soap will surround the dirt. And what it will do is essentially line up the polar part of soap on the outside. I'll just make a minus sign there on the outside of it, which is really good because it will kind of trap your dirt in the nonpolar part of soap, make a micelle. And what we typically do after we use soap is we wash it off with water, which is polar, which works really great for the other part of soap, which is on the outside now with your dirt trapped in there. So when you use water to wash, it will wash away the soap that has the dirt trapped in it and you're clean. Good to know how soap works, I suppose, right? These are good things. So what also happens though, if we have a nonpolar surface, for example, like your car, if it's been waxed, an umbrella, water will tend to bead, right? So water will tend to bead in that situation. And especially if you have a really nicely waxed car. and you put water on it, you'll just see all the beads of the water doing so. So it won't allow the water really to spread out because you have kind of that polar, non-polar interaction that's sort of happening. And that's why when we go to wash our car, we usually will wet it and then wipe it down with some soapy water. And when we use soap, what happens is the polar part of soap is able to get into and between the water molecules, and what happens is it will allow basically the water molecules to spread out along with the soap, and then obviously that will clean up all the dirt on your car and stuff like that. There used to be an old, I think it was Dawn commercial, maybe, like they have the really dirty, greasy in the sink, and they just do a drop of Dawn, and you see it all go and spread out and everything like that. And that's sort of the same idea. The soap, when it hit the water, allowed all the water molecules to spread out with the dirt and stuff like that. And so again, that polar part of soap able to allow that to kind of spread out. And again, that's sort of what happens when you kind of wash your car. Speaking of our adhesive and cohesive properties here, when we have a liquid in a glass tube with a small diameter, the water, for example, will rise through capillary action. And this is due to, again, the attractive forces between the liquid and the walls of the glass container. And that's that adhesive forces are greater than the cohesive forces. So what we get is, again, that curvature of the liquid as the sides of the liquid is basically crawling up the walls of the container. That is why in this case we read from the bottom of the meniscus, and we read from the bottom of the meniscus because if that attractive force wasn't there, nobody would be climbing, and the volume would actually be down there at the bottom of the meniscus. So that's why we take a reading from the bottom of the meniscus. Now, not all substances that's the case. Most substances you will see the sort of U version of a meniscus, but there are certain substances where the cohesive forces, the attractive forces between the molecule itself is actually stronger than the sort of glass container it's in. And mercury is an example of that. The attractive forces between mercury and itself is much stronger than the attractive forces between mercury and the container. So what happens is, in mercury's case, it actually comes in on itself. And in this case, we would actually read from the top of the meniscus, because without those forces, the actual volume would be back up in this area as well. So mercury is an example of that, although they pulled mercury out of most of the labs, so we don't really see it. But most of the time you'll see that U sort of meniscus, because of the adhesive forces, is much stronger than the cohesive forces, and you get that capillary action as it rises. Any questions on that there? So let's talk a little bit about vapor pressure as well. So at the surface of a liquid, you always have pretty much the same thing happening. And that is, as I draw a wonderful liquid surface, we pretty much got some fast moving liquid molecules that are going to jump out into the gas phase. And then you have some slower moving gas molecules that are going to drop back down into the liquid phase. So at the surface of any liquid, you basically have this sort of exchange that's happening. It will sort of reach equilibrium at some point. And the tendency of a liquid to go into the gas phase or become a vapor is what's known as being volatile, or the volatility of it. It does increase with temperature. And again, it's also increases with how weak those intermolecular forces are. So increasing temperature adds more energy. It allows those guys to separate from each other and go from the liquid state into the gas state. Remember, as you go from liquid to gas, that's an endothermic process, right? So you have to put energy in to do that. So obviously, if you increase the temperature, increasing the energy is going to make it a lot easier for something to go into the gas phase. Liquid in an open container will evaporate completely, because air will basically diffuse it. It's also why when we spill something, say on the countertop or something like that, a small little spill, eventually it will evaporate, because what happens is we do have that rate of evaporation that occurs. But in the case of this situation, you have air that's going to blow those guys away and not allow them to come back into the liquid phase. And eventually it will completely sort of evaporate. So if you put a little drop or so on the countertop, it is definitely going to evaporate a lot faster than if you put it into a container, right? In that case, there's a lot more molecules underneath the surface, but you will still have some of that rate of evaporation happening, but it's going to be much slower because, again, it's going to take longer for those guys to get there. There's also a much greater surface area for all that to occur on just the bench and a sort of wide open area. But regardless of that, as we have these guys jumping out of the liquid phase above the liquid, it is creating a gas, which is known as the vapor, and that is called the vapor pressure. So basically, the pressure associated with the gas molecules that are above the liquid is what's known as the vapor pressure. Liquids with high vapor pressure are said to be volatile because if they have a high vapor pressure, that means the only way you could get high pressure is to have a lot of molecules. And that means you have a lot of things that have now jumped into the gas phase. So clearly it's going to be able to go into the gas phase really easily. Something with a low vapor pressure is probably not going to be very volatile because not a lot of guys are jumping out of the liquid phase into the gas phase. So you don't have a lot of gas molecules above the liquid in that sense. The vapor pressure of a liquid at a given temperature is also determined by the intermolecular forces. Things with large intermolecular forces or strong intermolecular forces will have very low vapor pressure. So again, because they're held together very tightly by those strong intermolecular forces like hydrogen bonding, for example, it's very less likely that they're just going to start kind of escaping a lot of them out from the surface. And a lot less will escape from the surface, which means you have much lower vapor pressure that's happening. So this also occurs in a closed container. So if we did put a liquid into a closed container, we would have at the beginning where we filled it in, let's say the level is right about there, we would initially have a rate of evaporation that's going to probably start out the most. These guys are going to go and eventually, well, they're going to reach the top, which is now capped, which means they cannot escape. So at some point, they will start heading back in the other direction there to go back into the liquid phase. And eventually what will happen is the rate at which they sort of escape the liquid phase and the rate at which they're dropping back into the liquid phase. So the rate at which they go that way and that way, the rate will equal each other. And that will be when they reach equilibrium. And if you look really closely at a liquid in a container like that, you will probably notice that the level of that liquid has dropped a little bit from where it started. And that's because when it started, you had nothing jumping out of the liquid, but because you capped it off, you eventually have some guys out of there and you have some vapor pressure right above the liquid based on those gas molecules that have escaped the liquid portion. And frankly, at this point, have nowhere to go, but kind of bounce back and forth between the gas phase and the liquid phase. Any questions on that there? So obviously at the beginning here, the rate of evaporation would be much greater than the rate of condensation, which is the dropping back in, but eventually it will reach equilibrium like it does there in B. We could actually calculate some of this using this guy's equation here, and that is the natural log of the vapor pressure at the first temperature divided by the vapor pressure at the second temperature equals the delta H of vaporization. Delta H of vaporization is the heat of vaporization, and this is the energy that is needed to convert a liquid to a gas, or vice versa, a gas back to a liquid. By the way, that does occur at the same temperature. So when we go from liquid to gas or gas to liquid, that is at the normal boiling point as to where that occurs. It is exothermic in one way and endothermic in another. So when we go from liquid to gas, it is a positive heat of vaporization. So for example, for water, it's roughly 40.7 kilojoules per mole, give or take. And as we go from gas back to liquid, it's an exothermic process, which means it will be a negative value here. And once again, when you have a positive value for energy, that usually implies that it's an endothermic process, heat and energy being absorbed. And when you have a negative value for energy, that implies that it's an exothermic process. And delta H is basically the heat of a reaction, and that's the enthalpy of a reaction. So that's what delta H really stands for, is enthalpy. So we could use that, and we could use R, which is the gas constant, but it's actually the gas constant that involves energy. It's the 8.314 version of it, joules per Kelvin per mole. This also will usually bring up some unit issues, and that is because delta H is typically in kilojoules, and R is obviously, as you see there, in joules. So you do have a 1,000-fold factor there that you got to be careful of. You do have to convert one to joules or the other to kilojoules. You got to make sure they really are in the same units. This is 1 over our temperature in Kelvin for each of these, obviously here. So let's take a look at one here. The vapor pressure of water at 25 degrees Celsius is 23.8 torr, and the heat of vaporization for water is 43.9 kilojoules per mole. Calculate the vapor pressure at 65 degrees Celsius. So we can use, again, our equation here, which is our natural log of our pressure is equal to our delta H over R, 1 over T2 minus our 1 over T1 in this case. Now, truth be told, when you use this equation, it doesn't really matter, which ones you call ones or twos, as long as you keep the temperatures and pressure values that go together. So in this case, we will say that our vapor pressure at temperature 1 is going to be 23.8 torr. We will also say our temperature here, 1, is going to be 25, which we do need to convert to Kelvin, so we'll add 273 to it. We have our delta H in this case, which is our delta H of vaporization, 43.9 kilojoules per mole. And we're looking for what the vapor pressure is at our second temperature, that is 65, that we also need to convert there to Kelvin. So we'll take our 65 plus a 273, going to give us a 338 Kelvin here. So we do have everything that we need. You don't actually need to convert to atmospheres or anything like that. As long as you solve it here, we'll end up in torr, and I'm hoping we'll end up with this number. Let's see. So we're going to go with the natural log here of our first vapor pressure, which is 28.3 torr. We're looking for our second vapor pressure here. My delta H here is 43.9. I'm going to multiply it by 1,000, and that's going to convert it to joules. So it will work well with the gas constant that's in joules. So once again, that was in kilojoules. You don't want to leave one in kilojoules and again the other in joules. So if you multiply the kilojoules by 1,000, you're into joules. This is going to be 1 over our second temperature, which is 338, minus 1 over our initial temperature, which is 298. So we have everything we need to clean up the right-hand side. I'm going to do that first. I'm going to take 1 divided by 338. I'm going to subtract it from 1 divided by 298. I am then going to multiply it by 43.9 times 1,000. I'm then going to divide it by 8.314. So if I do all that good stuff, that's going to give me the natural log of 23.8 over our pressure, and that's going to equal minus 2.0969. At this point, I need to get rid of the natural log. To get rid of the natural log, I'm going to take the E on your calculator of both sides. And when I do that, that's usually above the natural log button on most people's calculator. We're going to do that. That will then get us 23.8. P2 is equal to 0.12283. By the way, when you do that with the natural log, it basically just cancels out the natural log part of it on the left-hand side there. So the natural log just goes away. At this point, I need to multiply the P2 to this side. So that will give me 23.8 equals 0.12283 P2. Finally, divide that guy back to the other side. So that's giving me 23.8 divided by that number there. Going to give me 194 torr. That's good. It came out to the right number. That would have been kind of embarrassing, I guess, if it didn't. Any question on that? So what we see here is, in this case, we increase the temperature, right? We went from 25 degrees Celsius to 65 degrees Celsius. And what happened to our vapor pressure? Did it go up or down? Vapor pressure went up, right? It started at 23.8 and now it's at 194. That is because with the increase in temperature, you have an increase in energy and you're going to have more liquid molecules that have enough energy to escape the liquid phase and go into the gas phase. And that means you'll have more vapor above the liquid, at this case, at the higher temperature, and thus you would have more pressure associated with it. Any questions on that calculation out there? All right, so continuing our journey here through liquid, let's talk about some processes that we're probably familiar with. Boiling, I'll spit that out, boiling. So when we do heat water to its temperature and it starts to boil, that obviously happens at its normal boiling point. And when we do start to heat water, for example, you maybe have noticed that if you take some water and you just heat it up really quick, you'll see a bunch of dots sort of happen on your water. Sometimes people think, wow, it's boiling really quick. And it's really not. Just that increase in heat really quickly makes the carbon dioxide that's in the water less soluble. So that's what you actually see come out, all those like small little bubbles or dots that sort of happen when you do that. So it doesn't really start to boil until you really get bubbles that can reach the surface. So what happens is, as you're boiling it, you will get some water vapor inside these bubbles. And if the pressure inside the bubble is less than the pressure outside the bubble, your bubble is not going to make it to the surface. It's going to basically pop before it gets there. But eventually you will heat it enough that the pressure inside the bubble will be equal to or greater than the outside pressure, and it will be able to actually boil to the top there, and you'll see your bubbles when you really know it's boiling, right? When the bubble can make it to the top. And then obviously when it gets to the top, it's going to pop and going to release that vapor pressure and going to start to boil. So when we get something that boils at its boiling point, that means we do have a lot of that vapor in there and the pressure inside equal to or greater than the atmospheric pressure. At lower temperatures, again, the bubbles really can't withstand the pressure and will start to pop. We call that its boiling point where we do boil. And that, again, is the transition between liquid to gas, and gas back to liquid is a normal boiling point. Once again, both of these transitions occur at the same temperature. So at 100 degrees Celsius, you have basically both phases happening at the same time. You have some liquid water, you have some gas. It's really not till you get, say, above 100 degrees Celsius that you fully do sort of transition something, in the case of water, into the gas phase. It's not really until you're a little bit below 100 degrees Celsius that you sort of really transition into the liquid phase. So right at 100 degrees Celsius, you basically have both things occurring. Now, we can raise the pressure. We'll increase the boiling point, like in a pressure cooker. In this case, we have a really tight lid on the pressure cooker, holds the pressure on the vapor above the water, and that results in an increase in the boiling point. So perhaps it will boil at 120 degrees versus, say, 100 degrees, which is like the normal boiling point in water. Pressure has an effect on things like boiling points and stuff like that, right? Which is, if you're like in Colorado, right, things will boil at different temperatures, right, than say down here, because obviously they're at a different altitude than we are over here. Boiling, oddly enough, is a cooling process. And sometimes people think that's the weird thing. It's a cooling process, but you are actually cooling out the top as fast as you're heating at the bottom. That's why if you ever put a thermometer in a beaker in a chemistry class and heated water, I don't know, maybe we did that. All right. Sometimes people used to freak out, like my thermometer only goes to 100. Is it going to just keep going and break my thermometer? And it's not, right? When you hit your boiling point, pretty much your temperature maintains at where it is. In an ideal situation, that would be 100 degrees Celsius, probably not in a real life situation. But that's because as you heat it from the bottom, you're losing a lot of energy out the top, right? And you're going to release a lot of energy at the top. And that's why when it hits the boiling point, it will stay at that temperature. Why, if you look at thermometers, they don't go too much over 100 degrees, a lot of them, because that's the normal boiling point. So although you are heating at the bottom, a lot of energy happening here, we got these molecules escaping and kind of cooling out the top. And again, that's why we don't see the thermometer just keep rising as you're boiling something. Eventually it will hit that boiling point and stop. The process, obviously, when molecules are converted from liquid to gas, is called evaporation or vaporization. Once again, that's an endothermic process, which means heat and energy needs to be put in. Condensation, again, is the opposite of that, where we take our gas molecules and convert it to liquid. The result of that is an exothermic process where heat and energy is released. And once again, because heat and energy is released, as these gas molecules fly around, they no longer have enough energy to escape each other. So now they're going to kind of stick and drop down into sort of the liquid phase. So as I mentioned before, at the surface of water, there's a constant sort of exchange of things going out into the gas phase and things coming back into the liquid phase. So when we have molecules that escape the liquid phase, they take a lot of energy with them. So it takes a lot of energy as they pick up that energy as you heat them to break apart from all those hydrogen bonding and work their way out of the liquid part and escape into the gas phase. The result of that is when those water molecules sort of escape the liquid phase, a lot of kinetic energy goes with them, which is sort of the cooling process that occurs for the liquid. Also, it's a cooling process for the outside of the liquid, the air, because now you got all these molecules that took a lot of energy to get out of the liquid phase, and now they're going to be moving much slower than the air molecules. So you're going to lower actually the kinetic energy of the air that's around it. So oddly enough, boiling is sort of a cooling process from that point of view. There's a net lower sort of kinetic energy that's happening in both places as you actually heat something to its boiling point. As water evaporates, the evaporation rate decreases. You can maintain the evaporation rate of water with contacting with a warm surface like your skin. This is why we feel warm when we take a shower. And if you take a hot shower, you have a lot of steam, right? And that means you have a lot of condensation that's going to happen. You can see that from the mirror, right? The mirror starts to get kind of all condensated up with the water that's in there. And as things go through condensation, which means it goes from gas to liquid, it is releasing energy. And you are currently standing there picking up all that energy, right? From the hot shower and all that condensation that's occurring. That's also why when you're done with your shower, or if you get out of a swimming pool, you feel really cold, right? And you feel really cold because now you have water on your skin. And when you have water on your skin, the process of evaporation is going to happen. And where the water is going to get the heat and energy from is you, right? It's going to take the energy from your body, right? And going to start to evaporate the water. You end up resulting feeling very cold and wish you were still in that warm shower probably at that point. So again, that is going to be a exothermic process for your skin as it releases that energy, and thus you will feel much cooler in that. So evaporation is also a cooling process. That's also why we sweat, right? When we overheat, when we get too hot, our body starts to sweat, because what it does, right, is it puts a lot of water on your skin, which increases the rate of evaporation, which will then pull energy out of your body and cool you back down, obviously, is why we sweat. Any questions on that there? So at the surface of water, condensation and evaporation is constantly occurring. Condensation occurs as, again, those slow-moving water molecules in the vapor phase really no longer have enough energy to escape each other. So we start to get some sticking that's going to occur. Faster-moving water molecules will bounce off one another, but those slower-moving ones will basically drop into the liquid phase. So in addition, you're removing slower water molecules when we have water vapor, and that means that we're going to increase the average kinetic energy. So condensation is sort of a warming sort of process as we do that, as it releases the energy. It's also the theory behind like the cold packs, hot packs, right? When you break them, when you break one of those cold packs, right, it does a endothermic reaction, which means when you put it on yourself, it's going to suck out all the energy from your skin and you feel cold. Also, when you have a hot pack, you break it, it's an exothermic reaction that occurs, which means when you put it on your skin's going to pick up all the energy and start to feel warm as you do that as well. Any questions on that there? So when we do these transitions, as we talked about there, that is the molar heat of vaporization. And that is, again, the energy to do those transition. And this is the value specifically for water. This is roughly 2260 joules per gram is how much energy is required. Again, at this point, it would be at 100 degrees Celsius, which is the normal boiling point of water. And exactly at 100 degrees Celsius, not changing the temperature or anything like that, to take something from liquid to gas or gas back to liquid, would require that amount of energy. Maybe from the previous class, you remember specific heat and specific heat capacity. That is the calculation, which is, by the way, something like Q is equal to ms delta T, which we don't talk about in this class anymore. We talk about in 200B. But that is the energy or the equation that we use when we change the temperature but keep the phase the same. We use something like the heat of vaporization when we keep the temperature the same but change the phase. So in this case, going from liquid to gas or gas back to liquid. It takes a lot more energy to do that transition of going from liquid to gas or gas back to liquid than it does going from solid to liquid or liquid back to solid. Again, if you go from solid to liquid, you still have molecules that are relatively close to one another, even in the liquid phase. But as you do that transition of going from liquid to gas, you have to completely break apart everybody from one another. So it takes a lot more energy to get everybody broken apart from one another. And that's why we see a very high heat of vaporization versus the energy required to do the solid to liquid transition. Just for comparison purposes, as was known as a delta H of fusion. And that is going from solid to liquid or liquid back to solid. For water, it's like 6.02 kilojoules per mole. So roughly 335 joules per gram. So a much lower amount of energy is required to change something from solid to liquid than it is to go from liquid to gas. By the way, as we'll talk about, going from solid to liquid, that occurs at a normal freezing point. Melting point is where that transition occurs. And for something like water, that would be 0 degrees Celsius as to where that would occur. And the same thing happens there when you're exactly at 0 degrees Celsius. You basically have both liquid and solid happening at the same time, like ice crystals sort of happening at that point. So as I mentioned before, that's sort of the idea there. When you're in that shower, you feel really warm because of that high rate of condensation. And then obviously you increase the rate of evaporation when you're done with your shower and you have water still on your body. So the rate of evaporation is going to kick into overdrive and you're going to feel really cold because of you got water pretty much all over your body at that point, and it's sucking out the energy from a lot of places. Now, freezing and melting, as I mentioned a second ago, is our transition that occurs from solid to liquid. And as we melt something, we're providing more energy. So it's an endothermic process. So you put heat and energy in, like an ice cube, which can just pick up heat and energy from the surroundings and start to melt. Freezing is the opposite. We actually release the energy. So when you take liquid water and you put it into the freezer, what's happening, right, is energy always goes from hotter to cold, right? And what happens when you put liquid water into the freezer is at that point, your freezer hopefully is much colder than the liquid water you just put in there. So all the energy is actually going to transfer from the liquid water to the freezer surroundings. The result of that is you're going to lose energy in your liquid water, and now you're going to have ice cubes for your beverages later. Yes, as you go to freeze something in that sense. So at 0 degrees, we do form ice, and we are releasing energy. One of the kind of strange characteristics of water is the idea that in its solid phase, it is much less dense than in its liquid phase. And that's because what we see here in this picture, this is basically like ice. And what happens again is when it comes together, because of that strong hydrogen bonding that happens in this solid form, it creates all this wide open sort of space between the different water molecules. If you think about density, which is mass over volume, that creates a much larger volume than a normal situation. And that means that on the bottom there, you have a larger number, which means your density will be much smaller than it is actually in the liquid phase. Those water molecules can actually, because they still have a certain amount of energy, can kind of get into each other a little bit closer than it can in the solid phase. That's an unusual property of a substance. Most substances, right, in their solid phase is much more dense than in their liquid phase. And that again is why when we put ice cubes in our cups, it floats to the top, right? When we have some type of liquid that's in there. Sublimation and deposition. These are processes where we go from solid directly to gas, skipping the liquid part, and that is sublimation. That also is an endothermic process where you have to put heat and energy in there. Deposition is the opposite, is where we go from gas back to solid, once again skipping the liquid cleanup along the way. Sublimation, you may be familiar with, dry ice, which is really carbon dioxide, it's not really water, is something that goes through sublimation. It goes directly from solid to gas, no liquid cleanup in the middle. DVDs, CDs, if you remember those things, they're shiny up on top, and they use the process. You could Google it later. We used to go to the store to get the DVD. I won't say go to the store to get the VHS video as well, but we went to the store to get the laser disc. Anybody remember laser discs? They're really big record-sized DVDs, basically. Never really took off because they were like the size of records. They're like giant. But how they got really shiny is they do a process of deposition. They kind of cool down metals there, and I guess what gives it sort of this shiny sort of structure. Once again, sort of a positive value for the delta H of sublimation going this way, negative value for delta H of deposition heading in that direction. So as I mentioned earlier, there is a certain amount of energy to do nothing more than change the state of a substance at both its melting point or freezing point or its boiling point. So once again, the heat of fusion, which is abbreviated delta H of fusion, that again is our value for water. And as we just mentioned there, we can see it is a much smaller value than what we see for our delta H of vaporization. As we were just talking about, obviously it takes a lot more energy to get everybody into that gas phase versus just going into the liquid phase. So I think this is a good place to stop right there. Any questions on that there?